All right, subscribers, welcome back to another episode of Science with Surbeck. Today, what we're going to take a look into is section 10.1, which deals with chemical reactions and equations. So, our objectives for this lesson is to 1. Recognize the evidence of a chemical change, and 2. Represent chemical reactions with equations. So, we start out here with what are chemical reactions. And chemical reactions are simply defined as the process in which one or more substances are rearranged to form different substances. And so what we talk about here with chemical reactions is chemical change. So with chemical change, we're going to identify how we can see or locate that chemical change. But the nice thing about this is that chemical reactions are occurring daily. They're occurring all the time, both inside and out of your body, all throughout the universe. So we have a lot of different great examples. So we start out here with how can we determine the chemical reaction has taken place? Well, we have some key indicators, and a chemical reaction is usually going to have one or more of the following. And that is going to be a change in temperature, a change in color, an odor emitted or a gas that's given off, or the appearance of a solid. Now, these are some common examples in which there is an indication where we have a chemical change. You can have a combination of these, or you can have some other unique things that are given off. The major thing to think about here is, hey, all right, is there a different composition chemically of the chemicals I started with and what I have here at the end? That's a major indication that we have a chemical change. Now, what's really important to us is how we represent chemical equations. And we do that, or we represent chemical reactions, through chemical equations. And so these are statements that chemists use to describe and really isolate these particular chemical reactions. So the major thing for us is this arrow. The arrow is going to separate our left and right hand side, and on the left hand side of the arrow is going to be our reactants, and on the right hand side is going to be our products. Now, when we have two or more reactants or two or more products, we separate them out by a plus sign. Now, this chart is very helpful in identifying what happens with our chemical equations. What we also need to get in the mind here is that the states of matter of each chemical substance in an equation needs to be represented. So you can see here we represent the states of matter by these following 4 symbols. Now, again, this is located in parentheses to the right of that substance that we are dealing with. All right, so word equations are how we are going to start our chemical equations. And so they are statements used to describe those reactions. Now, you can see here that we need to utilize our knowledge of chemical reactions to determine how we can write these particular equations. So we start out here with the simplest equation. We call this the skeleton equation. And what happens here is this. This is the statement that shows the products and reactants of a particular chemical reaction. So what we do here is very simple. We take the word equation and we put it in our chemical symbol notation. So what we're going to do, we're going to walk through this process. We've seen it before in an example, but I'm going to show you how the steps were done to get to that point in our equation. All right, so what we do here is we just read it first, and it's aluminum and bromine react to produce aluminum bromide. So aluminum, it is an individual element, and with an individual element, we have to remember to check and see if it's diatomic. Well, aluminum, element number 13 here, It's not diatomic, so all we do here is we write down Al. Now, bromine, if we find it on the periodic table, is Br. And remember, it is one of our lucky 7 diatomic elements. So it's diatomic, so that means we don't just write Br, but we write Br2. It is a diatomic element. And then it says react to produce. So whenever you see react to produce or yield or produces, that's our indication that we need to draw this particular arrow. Now, it says it produces aluminum bromide. Now, here is a key indication that we need to turn to our chemical substances or our ability to write ionic and covalent compounds to write this particular reaction. So, aluminum bromide, we're dealing with Al and Br. And remember, Al and Br are on opposite sides of the equation, or we have a metal and a nonmetal, which means we need to deal with charges. So Al, you can look this up. Al, if we look up its charge, is 3+. Now, Br is the symbol for bromide, and it had a charge of 1-. Remember, we switch or flip-flop the charge numbers to become our coefficients. So we would need 1 Al and 3 Brs. So we would end up with Al Br3 in our equation. And that's how we go from writing our word equation to actually having it in symbol notation. Now, this equation is not yet complete because we haven't balanced it. And that's the next thing that I'm going to show you how we can do. So, in this, before we get to that, what I want you to do here is this. I want you to pause and try to write these skeleton equations for these 3 reactions. All right, so if you're stuck here and you haven't figured out how to write these equations, here's how you do it, all right? So you have hydrogen and bromine. The first thing that you do is hydrogen. You look up, is it diatomic? Yes. That means you can't just write H. You have to write H2. Then here, I noted that we have the state of matter, which is a G for gas. So we're going to put that G for gas in parentheses. Now, bromine, we just got done looking at bromine on the other equation. So bromine is Br. It's diatomic, and it is shown here as a gas. This produces hydrogen bromide. Again, think to yourself, okay, is this ionic or covalent? Well, it's ionic because these elements are on opposite sides of the periodic table. One's a metal, one's a nonmetal, so we have H, 1+, Br, 1-. We flip-flop the charges here, and so hydrogen bromide becomes HBr as a gas. Okay, again, those equations aren't balanced, but we can work on that here momentarily. Now, we start out here, carbon monoxide. We see that we have a prefix, so that means we're going to go with the covalent bonding. So no prefix out in front, that just means the element C. Mono means 1. Oxygen for that is CO, and that's CO gas. So we put G for gas in parentheses. It reacts with oxygen. Again, symbol for oxygen is O. Always double check here. Your oxygen is what we call diatomic, so it can't be just written down as O, it has to be written down as O2. Now it produces carbon dioxide. So carbon dioxide, again, we see the prefixes, so we turn to our covalent naming protocol. We have C for carbon, only one of them because there's no prefix. Dioxide means we need 2 oxygens. All right, so that's how we would write our symbol there. And again, don't forget state of matter. If it's given to you, carbon dioxide is also a gas. Now, potassium chlorate. Again, this right here is a compound, and it's an ionic compound. So that means we're going to need to use our charges. So we have K1+ for potassium. Chlorate, if we look up, is ClO3 with a 1 minus charge. Now, if you forget here, you can look this up in that ion formula chart. So the ion formula chart here for chlorate is shown ClO3 with a 1 minus charge. So this means when we have potassium chlorite, it would be KClO3 as a solid decomposes into potassium chloride. Again, we have to worry about the charges. So K1 plus, if you look up chlorine, it would be Cl1 minus. So that would form KCl as a solid, and oxygen, O2, as a gas. Okay, so that is how we would go through and write this particular equations. Now, one thing we haven't done yet in these examples is balance our equations. So why we balance is we are showing that mass is conserved, and we need to show that by balancing the equations. So we need to have equal stuff, more specifically equal atoms on the left and right hand side. And so that's why we balance our chemical equations. How we balance it is by changing coefficients. We can't change those subscripts at all because we just went through a couple chapters of naming protocol and we would violate that protocol. So we have to put coefficients, numbers out in front. Key word here, out in front. Now, if we see a coefficient or we have a coefficient of 1, just know in chemistry we assume that a 1 is not written. All right, so here are the steps. The steps here is really a guess and check method. We can actually start wherever, but we're going to need to make sure that all atoms are equal on the left and right hand side of the chemical equations. So what we're going to do is we're going to pick one atom. Doesn't matter which atom that we pick, and we're going to balance these equations until every atom is equal on the left and right hand side. All right, so what we do here is this. We are going to try some examples of these particular equations. So it says write the balanced chemical equation between a reaction of hydrogen and chlorine that produces hydrogen chloride. Okay, so hydrogen, we looked that up and we see it's H. It is diatomic, so we have to write down H2. And it reacts with chlorine. Symbol for chlorine, Cl, but it can't just be Cl by itself. It's diatomic, so it has to be Cl2. This produces hydrogen chloride. So hydrogen chloride is a compound. We have to worry about charges. It's H1 plus and Cl1 minus. That would form HCl. Now, this is not balanced. So what we need to do is we need to look at this. We see our H. We have no coefficient, so we assume there's 1 times the subscript, so 1 times 2. This means we have 2 hydrogen. On the right-hand side, we have a coefficient of 1 times our subscript, which is also 1, so we only have 1. So this side needs a total of 2, and so what we need to do is put a 2 coefficient out in front. So this gives us 2 H's to equal our 2 H's on our left. Now Cl has 2 on the left by taking the coefficient 1 times 2, so 2 as our Cl. And then on this side, this coefficient also applies to the Cl. So we would have 2 times 1 for the Cl, so that would give us 2 Cls. That equation is now balanced. So let's go ahead and do this. We're going to take some time here and we're going to write these equations and we're going to balance them. So we start out here and it says in water, iron 3 chloride reacts with sodium hydroxide, producing solid iron 3 hydroxide and sodium chloride. So we got a lot going on here and we start out with this. Iron 3 chloride. Well, iron 3 chloride here is Fe3 plus and Cl1 minus. Okay, so iron 3 chloride, the formula for that would become FeCl3. It reacts with, so that's saying we need to add to that reactant side sodium hydroxide. Again, sodium hydroxide is Na, 1 plus. OH is hydroxide with a 1 minus charge, so it would be NaOH. And it produces solid iron 3 hydroxide. So we would have iron Fe 3 plus hydroxide OH 1 minus. So when we have that in formula, it would be FeOH 3. And it produces sodium chloride. So sodium is Na 1 plus, chloride is Cl 1 minus. And so that would give us NaCl. Now this equation is not balanced. You see here, we have to start with any element. I'm going to start with Fe. So the coefficient out in front right now is 1 times 1. So we have 1 Fe. Over here we have a coefficient of 1 and 1. So those Fe's right now are balanced. And we'll move on to our Cl's. Right here we have 1 times 3, which is 3. Over here we have 1 times 1, which is 1. So we need to put a 3 coefficient to produce this Cl as a 3. Now we move on to our NAs. Na, we have 1 over here on the left. On the right, we have 3 times 1, so 3. So we need to make this side a 3 by putting a 3 coefficient out in front. Now we have 3 times 1 oxygens, and this is 3 times 1 oxygen. This subscript applies to both the O and the H. Now, our coefficient out in front also applies to this H, so we have 3 times 1, which is 3, and this subscript applies to this H, so we have 3 times 1, which is 3. So that equation right there is balanced. Now, let's move on to our next example. So we have liquid carbon disulfide gas, carbon disulfide reacts with oxygen gas to produce carbon dioxide and sulfur dioxide. So we have prefixes. That means we need to turn to our covalent naming protocol. So carbon disulfide, we would have CS2. It is liquid, so we have to indicate that state of matter. It reacts with oxygen. Can't just write oxygen by itself. It's what we call diatomic. To produce carbon dioxide and sulfur dioxide gas. Okay, if you forget or you're wondering where I got these, it's all from the naming protocol we did last chapter. Okay, let's balance this, all right? So on the left side we have 1 carbon. On the right side we have 1 times 1 carbon. So the carbons right now are balanced. On the left side we have 2 sulfurs. On the right side we have 1, so we put a 2 coefficient out in front. And then we turn to our oxygen. Over here on the left we have 2, and on the right we need to be very careful because we have 2 oxygens from the CO2 and then 2 times 2 oxygen, so 4, so a total of 2 plus 4, which is 6 on the right. To get 6 oxygens on the left, we put a 3 coefficient out in front. Now we are balanced. All right, so this final problem here says solid zinc and aqueous hydrogen sulfate react to produce hydrogen gas and aqueous zinc sulfate. So we start out here with solid zinc. Well, zinc is written by itself. It's not diatomic, so we can just put Z in. It reacts with hydrogen sulfate. So hydrogen, remember, had 1 plus. Sulfate, if we look that up on the ion formula chart, we would find that we have SO4 with a 2 minus charge. So hydrogen sulfate would be H2SO4. It is aqueous, which you can look back on that table as AQ. It reacts to produce hydrogen gas. Hydrogen is H, but it's diatomic, so we need two of them. Gas, which is G, and aqueous zinc sulfate. So zinc sulfate, zinc always has a 2+ charge. Sulfate has a 2- charge, and so we would end up here with zinc SO4 that is aqueous. All right, so now let's go ahead, let's balance this. So we have one zinc on the left, we have one zinc on the right. We have two hydrogens on the left and two on the right. We have one sulfur, 4 oxygens, and 4 oxygens. So this equation right here is balanced. Now we spent a lot of work getting to that point, but because we wrote our formulas correctly, this is why this equation is already balanced. So this equation is already balanced. It would have coefficients all of 1. All right, so excuse me. The last thing here is just to emphasize why we balance chemical equations. We are abiding by the law of conservation of mass and matter by balancing our equations. This is our foundation point for chemistry. It's really a driving force to determine how much items will produce or reactions should produce, and if it doesn't, we need to explain what has happened. All right, I hope you have enjoyed this particular episode, and as always, make sure you subscribe if you haven't already.